So it gives me great pleasure today to introduce our keynote speaker, Dr. Greg Holland. Now, Greg is a Willis Senior Scientist in the Mesoscale and Microscale Meteorology Lab of NCAR. He's the Director of the Capacity Centre for Climate and Weather Extremes, C3WE. He has had a long career in meteorology, including forecasting, teaching, research, and community service, with the major focus being on weather and climate extremes and unmanned aircraft. His publications have included major contributions to 6 textbooks and forecast manuals, together with over 120 research papers. And Greg, actually, you were quite important in my own research for some of the papers that you wrote early on in your career, so thank you very much for that. As well as being incredibly busy in his professional life, I've also read some interesting things about him outside of science, one of which was that you were a professional dancer. Is this correct? Yeah, I did not know this. For many years, apparently. He's also an avid photographer and bird watcher, and can I confirm that you co-own a winery? Yes, so we... Yeah, damn it, because I was going to say we can talk later. Okay, so it gives me great pleasure today then to introduce Dr. Greg Holland, and he's going to talk on tropical cyclones and the global energy budget and their role and implications. Thank you, Greg.
Thanks. First of all, can you all hear me up the back because I'm wearing one of these mics? Is it okay? If it goes down, put your hand up and wave it around and I'll go to the other mic, so thank you for that. And thank you, Lisa. When you warned me that you might be saying something, I was really terrified you'd been talking to John McBride, but that's okay. I'd like to firstly thank you all for coming, and I do want to acknowledge the traditional Koori custodians of these lands and pay my respects to their elders. The talk itself is going to go into the way in which the subtropical energy budget actually defines the number of tropical cyclones. And this is quite a radical viewpoint that I've evolved over recent years, and it's only just recently we've been able to actually prove that this is almost certainly the case. So what I'm going to do is I'm first of all going to actually just lay out the problem, and then I'm going to give you my hypothesis that we started off with, and then I'm going to actually go through a Meteorology 101, just a very simple description of how the system works, because it doesn't necessarily work the way that your textbooks have told you. And then I'll go on and give you a whole bunch of data and things like that that will hopefully convince you that this is the answer. So where this all came from is, since I've been a meteorologist, we've talked about why is there 80 tropical cyclones a year? And you can see up on the top left-hand side there, it doesn't vary very much from year to year. So there is some magic thing that says, well, A, we're going to have 80, and B, they're not going to vary from year to year. If you look at the individual ocean basins in there, you'll see they vary a lot. So there's something interesting happening here. Now, many years ago, there was a paper which shows statistically that given those basins and their variation, you'd expect the global value to not change very much. But that's not really the answer, because there is cross-correlations between those different ocean basins, and in any case, the statistics didn't tell you why there's 80. It just said maybe this is why there's a really relatively consistent number. So the hypothesis I came up with is tropical cyclones are actually a direct response to the requirements of the tropical, subtropical, because it actually goes into the Hadley circulation as well, energy budget. If you take that as is, then you come to the obvious corollary, and that is that if that's true, because the subtropical energy budget doesn't change much from year to year, the annual constancy is actually then a follow-on. And I also done some easy back-of-the-envelope calculations which showed me that intense tropical cyclones probably contribute a lot more than the weaker tropical cyclones. Well, let's see how it worked. But first of all, a bit of a description of how this all works. What you see in this diagram, which is just it's just the outgoing cloud optical thickness in this regard, and the colours that are not blue are where there's clouds. And you can see the intertropical convergence zone sticking along the equator. You can see the the convection in the maritime continent north of Australia, and you can see an enormous area of blue. Well, what's happening is that the energy that goes up into the atmosphere is going up in the coloured areas that are not blue, and all of those blue areas are cooling every day of the year. And they're losing energy, and that energy's got to get transported out to those blue areas. There's another problem that we have this, the only energy that we get is the energy we get from the Earth's surface, which is mostly latent heat that comes in at the Earth's surface, and the energy that's going out is going out by radiative cooling, but you notice that we've got actually a minimum in the middle of there. So you can't just simply be taking energy up and out, because you can't take energy through a minimum without changing the minimum. And Joanne Malkus and now Simpson and Herbie Reel came up with the answer to this back in the 50s, and I'll show you how that works as well. So let's start with a very simple cross-section. We've got all this clear air out over here on the right, cooling at around 2 degrees C per day. We've got height up and a cross-section across. All of the energy that's available in the atmosphere is in that little equation there. We have thermal energy, temperature, then latent energy, potential energy, and then kinetic energy. And that little sort of curve shows you the minimum. Well, what Herbie and Joanne showed was that the tropical clouds, because they had a protected core, they just ducted the energy straight through. Now, that's not my idea, that's been around for many years and it's very well accepted. But you need to understand how that happens. The number of people I talk to that think, oh, that just pumps heat out the top and that's what you use. Well, that's not what happens. So let's go through it. We have latent energy coming in the low levels, goes up in the cloud. The cloud produces rainfall and cloud droplets, therefore you get a conversion from latent energy back across to thermal energy. That thermal energy drives a parcel which gives you vertical kinetic energy. The parcel goes up, the kinetic energy gets converted to potential energy, and actually what mostly comes out the top is potential energy. Now this is crucial to the whole process, because the latent heat that you picked up a long trip over the oceans in the trade winds, and it doesn't actually go anywhere until you put into a cloud. The potential energy up the top, it can go a long way because it's not going to go anywhere until it needs to. And what it does is it gets out into this region here where it's cooling. And as it cools, the air subsides a little bit. We get compressional heating. So you're basically converting potential energy back to thermal energy. This is the way the atmosphere works. And this is also what convective radiative equilibrium is. And I checked a few textbooks coming into here after a conversation with Christian Jacob earlier in the week, and the textbooks actually get this wrong. I'm going to really get into trouble over this one, but I guarantee they get it wrong. This is a diagram I stole from Christian. And here we have the bottom is the distance from where the convection is, and the grid size in the bottom row there. And you can see that if you're actually in the convection, there is an awful lot of convection being produced, but it nowhere near goes to zero. That's actually advected out. That's the GZ coming out the top and going away. And you've got to get out to around 5,000, that's a 50 by 50 degree box there. You've got to get out to about 5,000 kilometres before you actually get to a point where you're starting to approach equilibrium. And the reason for this, of course, is we generate a lot of heat, a lot of energy pass a lot of energy in the thunderstorms. We take that out, it's actually exported out, which breaks the radiative equilibrium rule. And then the air is used to actually balance the radiation out in these larger distances. So going back to that diagram, I've now added the little white line showing where the tropical cyclones are, and I just put a 5,000 kilometre line on there. So when I'm talking about tropical cyclones, don't think, oh, the cyclone was only there for a week and look at all that time that's got to be there. The energy that it puts into the upper atmosphere, GZ, takes weeks to go off and be used as to balance the radiation. But it doesn't matter. It's there. It just goes off. It takes weeks for the latent energy to come into the convection as well. And so basically, it's not the time scale of the system you're looking at. It's a time scale of what can be supported in the related circulations. So let's get down to the real nitty-gritties. We first need to understand how much energy flux there is in tropical cyclones. And to do that, we've first got to define what a tropical cyclone is. What you see in this diagram is a vertical cross-section with height and an energy flux on the bottom axis. And you can see that as you get further and further away from the center, you actually get more and more. But then once you get to about 1,000 kilometers, going further doesn't make much difference. So that little box that I'm showing you up in the left-hand corner up there, that's how we define the cyclone. It's sort of the area at which the cyclone is actually producing convection that's actually being exported it out. It's an arbitrary choice, but it doesn't matter if I chose 800 or 1200 or 1500, you're going to get the same basic numbers, so it's not a big deal. But that's what we chose, and that's why we chose 1,000 kilometers, which means, of course, there's a lot of energy being pumped in the spiral bands and things like that. It's not just the center of the cyclone. The data we're using the ERA interim, the JRA 55, they're both reanalyses. We've got a bunch of WRF North Atlantic forecasts, which you can see on there, which we use because I want to compare cloud resolving simulations with the reanalysis. And then we've got a simple little climate change, which I'll use at the end, that actually occurred over a scale in that box there, which I'll use at the end just to give you an indication of what might be happening in the future. So let me give you the answers. The tropical clear air long wave cooling, as I said before, is about 210 watts per square metre. That's not our work, that's other people have shown that well quite clearly. The actual amount of clear air in the tropics is about 65%. That's again not our work, though the work we did shows that that's a true number. And then what we've done here is we've got the total transport in tropical cyclones is 5,600 watts per square metres. And then we've got in percentages, the 2C contribution to the entire subtropical cooling, 25%. If we just look at the summer hemisphere, which is where I think this is really critical, it's something like 37% in the southern hemisphere, 62% in the northern hemisphere, and the proportion that's used in what we'll loosely call the tropics plus or minus 30 degrees is about 80%. So you can't neglect these numbers. I mean, these numbers are up there with the entire ITCZ of the North Pacific. Actually, they're higher than the entire ITCZ of the North Pacific. So there is something potentially serious happening here. We have on here is the colours are the actual energy being pumped up by those tropical cyclones, and it just shows you how it varies from location to location. And notice how big the contribution is in the Pacific. And indeed, in the Pacific, it's the major contribution by a long shot to the overall energy budget in that region. On the right-hand side is the black line is other convection, and the blue line is just the relative contribution from tropical cyclones. This diagram, the figures are a little bit out of date now, so they need to be changed. But the reason I show it to you, you can see that you've got these tropical cloud areas and the cyclones sit off to one side. So the cyclones are actually closer to where the radiative cooling is occurring, which means the numbers we're using are probably a little bit conservative when we're looking at the actual contributions that they can make. Here we have the Poleward energy transport, and we've got latitude running along the bottom, and we've got the two different analysis schemes there and the error bars on the analysis, which as you can see are quite large. But they both show exactly or a very consistent picture, and that is while the cyclones are in low latitudes, they don't transport much into the Hadley circulation. But as they get up towards the Hadley circulation latitudes and they get up into the 24, 25, maybe 30 degrees of latitude, they actually put about 40% of the total contribution to the Hadley circulation. So there's an awful lot of the energy goes just into the tropics, but as you get further north, it goes a lot more into the Hadley circulation. Did that change? Yes. This is just a quick comparison with the cloud resolving model, which is the WRF model up on the top. The left-hand set of figures are the vertical energy flux. We've got latitude running along the bottom. The right-hand set are the contribution to the poleward energy transport. In other words, just the bit that's going poleward. And I showed you the figure in the bottom right before. And you'll see that if we look at the total energy, vertical energy flux, the analyses don't do it too badly. The black line is the same in both of those. So it's getting about the same as what the fully cloud resolving model gets. So we're happy with their results there. But if you come over onto the actual Poleward energy transport, there are two possibilities here. One, that small data set for the WRF was picking up some anomaly, or there is actually an underestimate of the Poleward energy partitioning of energy for the reanalyses. We don't know the answer to that yet, but the point still remains that in both cases they show the same increasing proportion as you go up into higher latitudes. This is the ratio of Poleward energy flux, just to confirm that. The colours, the redder the colour, the more that goes into the Poleward. And you can see it's just basically confirming that no matter where you go on Earth, that this story is there. As you go further poleward in any of the ocean basins, you get more going into the Hadley circulation. And you can see an interesting difference here on the right-hand side, which is the WRF 4-kilometre forecast. If you compare that with the reanalysis forecasts up in the Atlantic, then you can see that there is actually quite a substantial difference in both amplitude and actual location. It's something we haven't resolved yet, but I'm just letting you know that it's there. But it doesn't change any of the basics of what I've been talking about. The next part of the thing was I had a hypothesis that the vertical energy flux was very much dependent on the intensity. Well, sorry, no, it's not. There's a very weak dependence, but it doesn't make a whole lot of difference whether it's a Category 5 hurricane or a Category 1. And I got to say that was a surprise. But then when I went back and rethought my calculations, I'd made too small an area around the core, so there it does make a difference. By the time you get out to the other sizes, it doesn't make much of a difference. And what does make a difference is the amount of rain that the cyclone precipitates. On the left-hand graph here, you've got precipitation on the vertical axis and vertical flux on the right axis, and there's one hell of a relationship. You'd expect there would be. Where's the energy coming from? It's converting LQ, right? Up on the global view, you'll see that that basically works again wherever you are. You've got basically that information, and the places where you've got more tropical cyclones, of course, you've got a higher proportion of precipitation. There's another thing hanging around in here, however, and that is that there is a dependence, and the dependence comes when we actually look at the column relative humidity. So now we've got the same sort of graph on the left-hand side, which is precipitation, column relative humidity across the axis here. And you can see that below about 60% column relative humidity, there's essentially no energy transport. As you get to higher and higher column relative humidity, it climbs up quite rapidly. And the colours up there show you the precipitation, and you can see how it dies off as you get away from the deep tropics. And essentially what is happening is there's two things here. Firstly, if you happen to have a lot more rain, you're going to have a lot more column relative humidity because you've got a lot more interchange and export out of the thunderstorms. The second thing is that as you move towards the poles, you actually move into the subsiding branch of the Hadley circulation, and that actually dries the surrounding air. And you can see that in some cases, which I don't think I'm showing here, where you can see it drops down as you go into the descending branch and then comes back up again as you move out of it. So column relative humidity is a significant component, intensity is not. Oh, and sorry, that's just a comparison. Now, just to emphasize, I would actually put away a question, and that is there's actually not much of a relationship with sea surface temperature, especially compared to the column relative humidity. And if we haven't done this properly, but we are going to do it, and if we take out the column relative humidity correlation, I bet you that SST one goes away. So whatever relationship there is there is because the warmer SSTs have got more column relative humidity above them. So the physical thing is the column relative humidity. Why should column relative humidity matter? It's not a trivial question, and it turns out to be a trivial answer, an almost trivial answer. This is not our work. This is taken from a study by Xu and Wang, and you can see they just ran a model and they changed the environmental column relative humidity, reran it so that it had a case study. They did it again, they did it again, they did it again, and what do you get? Actually, this is Hill and Lackman, and they get a smaller tropical cyclone with low column relative humidity, a bigger one with high relative column relative humidity, and Zhu and Wayne get the same result. That's where I was wrong. So basically, it's not just the fact that it's column relative humidity, it's because it actually influences the size, which means it influences the number of vertical columns that are taking this energy up, and ergo, I might add, the rainfall. And so we think that's the reason that there is such a variation in these particular storms. Is there some way that you could actually maybe work out that they have to be a certain size? If they're not a certain size, there have to be more of them. We haven't gone down that path yet. Future climate. I'm going to emphasize this is based on a small simulation, and it's not very many cyclones. There's only about 20 or 30 cyclones in each of the time periods in here. But you can see the current from that simulation, the vertical energy flux versus latitude at the top, the column relative humidity to the middle, and the poleward transport to the right. And you can see, let's start on the right-hand side first. You get the same basic information. In other words, as they move poleward, they petition more into the poleward transport in both future and current climate. There's a bit of a difference there I'll come back to. Looking at the column relative humidity, you can now see that curve, that drop-off I told you about. As you come up into about the 30, 35, 40 degree range, column relative humidity drops off, energy drops off. You know it drops off because of the relationship, and then it climbs back up again. And the vertical energy flux, you can see the relationship between the two there. So basically it's showing the same response, the same basically results, the same general information that we've been talking about. And I think this is going to turn out to be correct in the future. But I can't guarantee it, but we are going to go on and do this with climate models, and basically we'll be able to give you a lot better information on that in the future. But for now, my fairly strong feeling is that they're not going to change very much. But there's something else hidden in here. A couple of things hidden in here, actually. First, let me show you this. Notice how there is a changeover between a sharp gradation, I guess, between the vertical energy flux and in current climate and the vertical energy flux in future climate as you go past about 35 degrees latitude. The red one tends to be with or maybe below or maybe just a bit above the blue line, but then you get over onto the other side and there is a lot lower amount of energy flux and transport in future climate. It's something we haven't investigated yet, and I suspect we won't get to it, but I would suggest that it's something else that is important. But there is another thing hidden in here, which was actually a nice proof of the overall process, and that is, if you look at those points I showed you before, now we have column relative humidity versus vertical energy flux, and the reds are the future climate and the blues are the current climate, and the relationships are actually quite solid, as you can see by the amount of by the correlation coefficients there. And the important point is that in future climate, you actually require less vertical energy flux to satisfy the budget. That means one of two things. It means that either the convection is more efficient, being the surface is warmer, that's probably a good answer, but the convection is more efficient, or they're a bit bigger, but I think that's probably not the answer. Or the fact is that there has been a change in the need for there's been a change in the actual radiative cooling in the external environment. And there is quite possibly a change in the radiative cooling because what happens in future climate is you get more moisture in the atmosphere. So in the part of the atmosphere that's got more moisture is a heck of a good greenhouse gas, and it actually keeps the warmth in. So it's possibly a couple of those things, and it's something, again, that we will look at. But just at the bottom line, I just want to emphasize, one other thing here. The other thing that comes out of this is if that is actually a true statement and that holds up in other things, it tells you need less tropical cyclones in future climate. And what is all the numerical models producing right now? They're producing less tropical cyclones in future climate. So I think there's a lot of consistency starting to come out. But whichever way you look at it, current climate or future climate, the energy budget requirements are actually really remarkably quite close rather than remarkably different. So I think I'm getting, how am I going on time? Yeah, 6 plus 5, so I'm about to finish, so start thinking up the questions. I'm going to actually firstly just re-emphasize this diagram here and basically point out yet again that they make a substantial contribution. If you took the tropical cyclones away, then you'd have to rev up the other convection substantially. If you revved up the other convection substantially, maybe the tropical cyclones would go away. I don't know, I suspect not. But I think the tropical cyclones really have such a contribution. We can't say that they're not an important component of that overall budget. And then I'll come to the conclusions, which will take me a little while. The question was, why there's only 80? The hypothesis was that they're a direct response to the requirement to balance the subtropical energy budget. I haven't proven that, but I've given you some hell of a good evidence. How we're going to prove it is we're going to now go on and make some idealized modeling studies. It's actually, I think, fairly easy to do, but every time I say that, the model bites me, so we'll see. But the way I would do it, and I think my colleagues agree, is we'll actually we'll just arbitrarily change the radiative energy cooling in the clear air. It's an easy thing to do, and see what it does to everything else. Does it change the convection? Does it change the number of tropical cyclones? At least that's the first step we'll do, and then we'll see where we go from there. But I think I'll be amazed if this doesn't turn out to be the reason for this particular process. The annual constancy, if you get the first one's right, the second one's right. It's not an arguable fact. Whoops, what did I do? There. And this one was completely wrong. I mean, there is a little relationship, it ain't enough to worry about. It's about a 5 or a 10% relationship as you go to more intense cyclones. But there is a really big contributor from the environmental within the cyclone column relative humidity. So I'll stop there and ask for questions, but I'll just finish. Well, before I finish up, I'll say this also, and I'm going to pass you to Christian if there's any really hard things, because he's a really smart guy and he knows more about this than I do. But this also shows that while your textbooks do convective radiative equilibrium, they're actually not doing it right. Convective radiative equilibrium does not occur in the convective region because there are substantial transports in and out of that convective region. You have to go to a large scale for that convective radiative equilibrium to work. And once you get that, the rest of this is physically quite consistent and basically inarguable. Thank you.
Okay, thank you very much, Greg. So we have time for questions. Have we got some from the floor? Mary, here. Hold on. Have we got a runner? No?
Thanks, Greg. Presumably you can use your budget calculations to, for example, predict how many tropical cyclones there should be at the height of an ice age, and then maybe compare that with what a model might say about the number of tropical cyclones at the height of an ice age, or something like that.
The answer is yes. All we have to do is be able to make sure we get the radiative part of the energy budget right in the ice age as well. So there'll be some assumptions in there, but yes, of course. By the way, I just want to emphasize again, notice there's actually not a sea surface temperature requirement here. Sea surface temperature requirement comes for other reasons, not because of the tropical cyclone.
Question here.
So I wonder if you could speculate on whether the percentage contribution to energy flux from tropical cyclones would remain the same under a warming climate.
Sorry, the actual...
The percentage contribution to energy flux of tropical cyclones,
Yep.
Would you expect that to remain constant under a warming climate?
Yeah, you can see that in the in a recent figure that I put up here. Just let me find it. There we go. Given that the radiative energy flux out of the clear air is the same in the future climate, let me start at that thing, then you can see the cyclones provide less energy for that. But that doesn't mean that there's not more cyclones. Sorry, that doesn't mean that the radiative energy flux has stayed the same. So if the radiative energy flux changes, then it'll change that proportionality. But just looking at how close those lines are, it doesn't change much either way, is the real answer.
David?
Okay, David?
Greg, thanks for a very nice and simple explanation of a question that's been important for a very long time. But how much does your analysis relate to the fact that in climate models, tropical cyclones are very poorly resolved or not resolved at all,
Yep.
and yet the energy balance is approximately balanced in most climate models? So given they don't have tropical cyclones, do they ramp up the convection to do the same stuff?
They do. If you look at the climate models, it often gets tuned out, but we've run a bunch of climate models as well. You look at the tropical convection, actually we saw a couple of talks here that even showed this. The tropical convection is actually raining higher than it should.
And the question from John McBride is, do you remember what happened at Jimmy Watson's and the Italian Waiters Club?
The answer is, what little I remember was you guys left me in the toilet and wandered off and I couldn't get home.
Okay, we have a question down here. Andrea?
Trying to get my composure back now after that story. Could you tinker, or should you be able to tinker with the tropical cyclone numbers if you ramp up or down the run-of-the-mill daily convection in the tropics? Because they would also feed a lot of energy into the budget, shouldn't they?
Yeah.
Because it's there every day.
Yeah. Well, as you can see here, those run-of-the-mill convection, which includes the Madden-Julie oscillation, easterly waves and everything else, are feeding in the summer hemisphere around about 50%. The point is they're not feeding in 100%, which is what people were saying before I started doing this stuff. Could we fiddle with a convection? Yes, you can. But you know as well as I do, every time you fiddle with a bloody convection in a climate model, all sorts of hell goes loose. So I'm going to start simple and play around with the dry bit, which is the radiative component, which is actually fairly easy to change. And all you're doing is saying, I now need more radiation, or I now need less, I need more GZ or less GZ, and then see who supplies it. So that's the first step, but yeah, you could go in and fiddle if anyone knows how to do that quite well, see me afterwards, because I'd love to try it, but I've been bitten so many times.
One here, and then go over to Christian.
Hi, Greg. Yeah, very interesting paper and discussion. One of the things I've been thinking about is in the Australian context, we see quite a few of the big monsoonal loads that I think in a climate model would be very hard to distinguish between the tropical cyclones. And so I'm assuming you'd lump all of those, including the ones that form over the Northern Territory and Kimberley, into the tropical storm category?
Yeah, it's a good point. It's not just Australia, of course, but Australia's got the most frequent ones. The answer is, it's something I think we should seriously think about. The biggest problem you got is you guys don't give us tracks. So we'd have to do an awful lot of work going back through satellite data and things like that to even get the tracks and get that information back out. So that's the biggest problem. But the good thing about the cyclone is we go to the reanalysis, we've got the IB tracks, we know where the cyclones were, we just check what the reanalysis did in that region. But it's a good point. I might add the Madden-Julian oscillation is another big elephant in the room in all of this.
Hi, Greg.
Where are we?
Chen here.
Oh, yeah. Hi, Shia.
So I assume the WRF simulation you use is uncoupled atmosphere model, right? Without ocean.
The WRF is a set SST, yes.
Right. So so in that case, there are probably some energetic issue there because tropical cyclone induce upper ocean cooling, and then that reduce energy by 30% to 40% easily.
Yep.
So in that sense, the fact that WRF rains twice as much compared to observations that already tell you that WRF calculations probably overdo energy, the one that you showed. That's one comment. So I do have a question then. So Jim Holton's calculation in his book chapter about transport energy from the tropics to the polar region require about 4,000 to 5,000 cloud clusters without taking into account the tropical cyclones. Although there is a direct number that the only 4 to 5% of a tropical cloud clusters spin into tropical cyclones. So it's part of that population. So the question is really, we need about 4,000 to 5,000 cloud clusters to transport energy. With tropical cyclone, it's part of the natural system, but why 4 to 5% of cloud cluster transport cyclone? So that means the requirement could be 5,000 cloud cluster without tropical cyclones.
The answer is I really don't know why a certain percentage of cloud clusters turn into tropical cyclones, and any more than I know why a certain percentage of easterly waves, which is essentially the same thing, turn into tropical cyclones. I suspect that what it is, that the tropical cyclone does actually need a finite amplitude disturbance, and I know a lot of other people have said the same thing. And basically, they provide the finite amplitude disturbance. So if things aren't being satisfied and you need this big, ugly monster coming through, then it's going to actually pick one of them and say, let's go. And in the Pacific, it picks a lot higher fraction than it does in the Atlantic, for example, and that's because the Pacific is a bigger area, I presume, but I'm guessing now. On the WRF runs, the answer is no. The reanalysis doesn't actually see the cooling by the tropical cyclone. The reanalysis doesn't see that at all, and in any case, the cooling by the tropical cyclone is only going to change the intensity a bit. It doesn't change the size, and so basically, as you saw in that in one of those figures, the intensity makes a little bit of difference, but not much. So I don't think that's an important issue. The important issue with the WRF model is that we are using the same, well, we're using the future SSTs and we're specifying them in the future climate. So, you know, there's other things that kick in there, but I suspect that they're fairly small and in the noise level.
Two last quick questions and then wrap up.
So, Greg, one question that immediately arises from your hypothesis is why can't ordinary convection balance the energy budget? Do you have any ideas yet?
I've got no bloody idea.
All right.
Well, no, actually, I'll go a little bit further than that. I've thought about it. I don't have any idea, but when you think of where the convection occurs, it can only occur for other reasons in a fairly narrow band in the tropics, called the ITCZ. It can only occur in big lumps in places like the maritime continent because there's islands everywhere. So there are some anchoring parts for the convection. So I think that I'm happy with the fact you just don't expand the area of the convection, but why doesn't the convection rev up and go a bit faster, or why isn't there more easterly waves, or why isn't there more MJOs? That I don't know.
Okay.
Okay, and one very last quick question at the front here. Thank you. Matt.
So, Greg, what role do atmospheric aerosols in the Western Pacific play in this energy balance? We don't see significant variance between necessarily between tropical cyclones in different oceans, but we know that there's significant differences in the energy radiative balance due to atmospheric aerosols over the Western Pacific.
Yeah, the atmospheric aerosols, as you well know, are generally pumped into the lower levels. This is generally an upper level situation. That's not to say there's not some up there, but they're in the lower levels. They're also soluble. So they don't get pumped up in the cloud. As soon as the cloud gets water, they get washed out. So you don't get a big change in that regard. And also the atmospheric aerosols in the Pacific are very much like the aerosols that we were pumping into the air back in the 40s, 50s, 60s until we cleaned everything up. I think that's the general view. It's not my particular view that they're actually balancing a large slice of the carbon emissions that China and East Asia are making as well. So I think its role is more there in the sense that it's actually holding back climate warming in that region rather than being a significant component to tropical cyclones. And the final point I'll make is that the tropical cyclones are actually forming a long way from there. By the time they get up into there, if there's an influence, it'll be happening then. But I can't see how it's going to actually change the outward kinetic energy transport from the cyclone. I don't say that someone might come up with a theory that says it does. Thank you.
All right, thank you. And can we thank Greg for that very interesting talk?